Hello everyone, my name is Mortaza Hosseini from University of Maryland, Baltimore County. I'm going to present QSNAS, which is a systematic approach to explore the best quantization and scaling factors for a neural network architecture that results in the least energy consumption per inference when deployed to a hardware. Let's quickly jump to what we are seeking. Consider a convolutional layer that has a 3D input feature map operated on a 4D filter and results in a 3D output feature map. Let's impose two other variables to this layer, namely a quantization level for every pixel value and a scaling factor that scales the number of filters per layer and correspondingly the number of channels per feature map. Traditionally, convolutional neural networks are made by stacking these convolution layers, and as a result, the model size and the feature map of our neural network is proportional to QS squared and QS respectively. The computation is also proportional to S squared. We know from a hardware fact that the power and utilization costs of multipliers and adders in FPGAs are proportional to QS squared and Q respectively, provided that multiplier and adders are synthesized using lookup tables and not DSPs. Now defining the problem statement, which is an optimization problem with two variables to explore, such that when the neural network is deployed to a hardware, the energy per inference is minimized and a target accuracy is met. The solution to this problem lies at understanding the behavior of both the energy and the accuracy functions. To start with, we selected a VGG-like architecture for CIFAR10 and SVHN datasets. We downscaled the neural networks from 1 to 1/8 and upscaled the quantization from 1, which is a binarized neural network, up to 8 bits, and we jot down the accuracy per experiments. We adopted a rational polynomial and used a least square error method to fit this function to our 16-point experiments. These are how the fitting serves look like. For the CIFAR10, the root mean S-square error is only 0.7%, which indicates a good fit. Now let's test a new pair of Q and S equal to 3 and 1/4 respectively. For CIFAR10, the model predicts 84.1%, while the actual accuracy is 84.2%. More interestingly, when we plot the accuracy contours for these two serves, we have a better visualization of how the accuracy of the two models behave with respect to Q and S. Next, we designed a hardware that accommodates the neural network and implements it for inference. There are a sequence of equations here that I skipped to mention that leads us to conclude that the energy per inference for a deployed neural network of Q and S can be approximated with a polynomial with 4 terms, as denoted here. In a nutshell, the first term reflects the computation energy resulted from multiplications. The second term is partly contributed by the computation from the additions and partly by communication from the model parameters. And the third term is resulted by communicating from the feature map, and the last term is resulted by the static power and the components in hardware that are irrelevant to Q and S. On a Z board from Xilinx, the 16 neural networks with different Q and S were implemented, and energy per inference were measured for each deployment. 4 of the experiments failed to be implemented because they overutilized the FPGA resources. For the remaining 12 points, fitting them to our proposed polynomial resulted in an RMSE of only 9.7 microjoules. When we tried the new neural network configuration with Q and S pair equal to 3 and 1/4, the polynomial predicted an energy consumption of 154 microjoules, while it was measured actually to be 140 microjoules. So back to the drawing board, we had an optimization problem. We approximated both of our unknown functions with respect to our two variables. Now, minimizing the energy in this system of nonlinear equations is as simple as taking S as a function of Q and accuracy, plug S in the function energy, and minimize the energy with respect to Q given a target accuracy. When plotting the function of energy with respect to Q and accuracy, we see these beautiful convex curves that state different quantization levels result in the best energy consumption given different accuracy levels. We look for well-posed pairs of Q and S that result in moderately high and low accuracy levels, such that Q is a natural number near the local minima of these convex curves, and S is a power of 2, and the selection of both of which do not overutilize the FPGA resources. Compared to the literature using the same VGG-like neural network with different quantization and scaling factors, our selected optimized neural network configurations deployed to the low-cost tiny FPGA from the Z board resulted in accuracy levels higher or on par with those of the related work, while giving the least power dissipation and the highest inference per joule. With this approach, we are now seeking the best selection for Q and S in mobile net versions that result in the least energy consumption per inference when deployed to either FPGA or ASIC. And that's all from me. Thank you for your attention. Stay safe and please send your comments and feedbacks to our email.